So then we went on to talk about constitutive modeling, the relationship between stress and strain for an elastic material. And since the stress and strain tensors are symmetric, they only have 6 unique components. You can write them in this sort of vector form. And then you have this matrix that has 36 entries that relates the stress to the strain. Of those 36 entries for a material that has no planes of symmetry, you can show that 21 of them are unique. So 21 material constants for a material that has no planes of symmetry. However, if you start adding assumptions about planes of symmetry all the way to the fact that an isotropic material has infinite planes of symmetry, then you get it down to 2 independent material parameters. Right? And in this case, the ones we use are Poisson ratio and Young's modulus. It doesn't matter which 2 you choose, and I'll show you a table that they're all related for isotropic materials. In terms of bulk modulus, shear modulus, they're all related to each other. They all have relationships between them. Okay, so going back to our tensor notation, then in matrix type notation, we can also write this equation very compactly. Right? So here we're saying that in terms of the bulk modulus and shear modulus, S is the bulk modulus times the volumetric strain. The volumetric strain is the sum of the diagonal entries of the strain tensor, right? We saw that. Times I is just the identity matrix, right? Plus 2 times the shear modulus. And this thing, is sometimes called the deviatoric strain. So it's the total strain minus 1/3 the trace of the strain tensor, right? So this 1/3 the volumetric strain is a measure. Remember we called that the dilatation. Right? So this is like a measure of the isotropic compression of the sample of a material. And so what's left, so if you take the total strain and you subtract off the isotropic part, what's left is the so-called deviatoric part, right? And that's the name for this. So this is a measure of like the shear strain in the sample, right? So it makes sense. You have like a shear modulus times a shear strain. Right? So you have remember when we're talking about the different material properties, right? The bulk modulus is a measure of the material's resistance to hydrostatic compression or expansion. Right? So you have the bulk modulus times something that's a measure of the dilatation, right? And then you have the shear modulus times something that's a measure of the shear. So again, the shear modulus is related to the Young's modulus and Poisson ratio through this relationship. And then there's also something that we call Lemay's constant. Usually we use lambda. And it's related to the bulk modulus and shear modulus through this relationship. And if you plug that back into that equation and just simplify it, then you get this guy. And it's sort of the most compact way you can write it. Okay, so there's a bunch of relationships, right? So there's tables like this. I think on Wikipedia or whatever, you can use the notes too, but they relate. So the way you read this is like, if you over here, if you know these 2 constants in this column, right? So if I know the bulk modulus and Poisson ratio, then I can just look across here and read off the relationship, right, between any of the other ones. So this is obviously it's the bulk modulus, Young's modulus, that Lemray parameter, shear modulus, Poisson ratio, and this is something that's related to I forget what's the name for this thing. This is not common, and this is only in sort of a this is not common in mechanics to use this, but this one you can get from the seismic measurements, seismic modulus. That's what it's called. Yeah.
Doesn't that kind of look like the factor that you multiply the matrix with? Like the one at the bottom?
This one?
Yeah.
Is it exactly? It's not exactly it, right? It's well, yeah. I mean, I guess it would be this term, these three terms, right? That would be M, M, M. I'm so used to working with tensors that I typically just think of them like that. So anyway, there's a whole bunch of these. That's only half the chart. There's the rest of it. So the seismic modulus is related to. So this is the P wave in the material, and so this is the P wave speed, right? P wave speed, which you can measure, is the seismic modulus over the density, and then the shear wave speed is the shear modulus over the density. It's the bulk density. Yeah, I mean that's all you can really measure unless in the ground, right? So you take it out, then even then it's fairly hard to sort of separate the pores from the rock itself, right? And test the true grains of the rock. It's fairly difficult.